Hi, on this recorded discussion, I'd like to talk about the chemistry of carboxylic acids. So carboxylic acid has this particular template, RCOOH. So it contains what we call the carboxyl functional group. So when it comes to nomenclature, carboxylic acid is the most senior. So whenever it is encountered in a structure, it's almost always the case that the structure will end in oic acid, since um, it's the functional group that will be taken as the priority among other functional groups. So take for example this compound. So in this case, it contains a lot of functional group. We have an amine, we have a ketone, a thiol, an alcohol, and an aldehyde. However, in the presence of a carboxylic acid, so I'd like to emphasize also that carboxylic acid might look like a simple carbonyl compound because of the presence of a carbonyl group. However, the chemistry is different so long as that carbonyl structure is directly bonded to hydroxyl group. It is technically a carboxylic acid. Take notice that ketones and aldehydes are or would take less precedence when it comes to nomenclature, owing to the fact that they are different functional groups. So in this case, because we have identified that carboxylic acid is the primary functional group, we count starting from the carbon of the carboxyl group as locant number 1, so 2, 3. So at location number 3, so instead of this compound as a thiol, this is now a mercapto to indicate that we are utilizing the prefix of the compound or prefix of this functional group. For locant number 3, instead of an amine, this is an amino. For locant 4, instead of an one, for ketone, this is already an oxo. For carbon number 5, we have a methoxy group. Carbon number 6, instead of an alol for alcohol, this is now hydroxy. And for carbon number 7, instead of al for aldehyde, this is also an oxo. Try to remember that for aldehydes and ketones, they have the same prefix. So the formyl group is just a specific case whenever we have only two functional group. However, more often than not, oxo is the preferred prefix for aldehydes and ketones. So you can encounter this as the you'll encounter this particular example that both at carbon number 4 and carbon number 7 they are called dioxo substituent. So the complete name is 3-amino, 6-hydroxy, 2-mercapto, 5-methoxy, 4,7-dioxo heptanoic acid. So carboxylic acid is very ubiquitous when it comes to chemistry, both in organic and biological chemistry, which is why even though we have now the modern IUPAC system of naming in which the same structure is present, we named it according to the number of carbon, the saturation between those carbon, and the usual suffix of oic acid. So the older version is still utilized up until now because of its popularity. So the name or the structure of this common name has two parts, the Latinized name plus the suffix ic acid. Take notice the only difference is the presence of O from the IUPAC oic acid. So for example, methanoic acid is also known as formic acid. So formic acid was initially discovered from the secretions of ants to deter predator. So the Latin name for ants is formica, hence formic acid. For ethanoic acid, a 2-carbon containing compound present in vinegar, its other name is acetic acid because vinegar's Latin name is acetum. For propanoic acid, for 3-carbon containing compound, initially it was isolated from milk. So the Latin for the fat present in milk is protospion and hence propionic acid. So take notice for propionic acid, it's almost similar. It's propion instead of propan. However, they may sound similar, but they have very different etymology. So another is butanoic acid. So its other name is butyric acid because it was initially found in butter, which has the Latin name of butyrum. Again, very similar sounding names, but different sources or etymology. And the pattern continues for the rest of the common carboxylic acid. So take notice, these are homologous series. So the only difference is the presence of another carbon in the structure. So another common carboxylic acid are the dicarboxylic acid. So this represents two carboxylic acids. Try to remember carboxylic acids are terminal functional group. So you will encounter the carboxylic acid in this particular structure at the tail ends of the linear structure. So both ends of the structure. So because of the presence of two carboxylic acid, so the suffix will now be a dioic acid. So utilizing the modern IUPAC naming system, so we name it according to the number of carbons. In this case, it's F. Then the saturation, so all of these are single bonds, so it's an an. And try to remember that for this particular case, the initial letter of the suffix is a consonant. So two consonants should not be placed one after the other, which is why we need to put back the E in the saturation portion of the structure. So this is ethane dioic acid. And the pattern also continues for other increasing carbon analogs of bicarboxylic acid. On the common name, so ethane dioic acid, also known as oxalic acid, propane dioic acid, also as malonic acid. And not to worry, because dicarboxylic acid's ubiquity in organic chemistry, there's this common nomenclature just to remember the name of the oh, to determine the common name of the stock. Because of the ubiquity of dicarboxylic acid, there is this popular nomenclature just for us to remember the common names of these compounds. So the mnemonic goes, oh my, such good apple pie. So the first letter of this phrase represents the first letter also of the common name. O for oxalic, M for malonic, S for succinic, G for glutaric, A for adipic, then P for pimelic or palmic acid. Another common dicarboxylic acid are those directly bonded to benzene ring, also known as aromatic dioic acid. So the only difference is their placement. Therefore, these structures are isomers of each other. So phthalic acid is the ortho isomer, isophthalic is the meta isomer, then terephthalic is the para isomer. So when it comes to carboxylic acid derivatives, so these are structure derived from the prototypical carboxylic acid structure. The difference between these derivatives is what's being replaced in the hydroxyl group, which is why we need to familiarize ourselves with the acyl nomenclature, because try to take notice that what remains with this particular part of the structure. If this is replaceable, so we need to make sure we know how to name this particular part. So these are called an acyl group. So we've encountered this also in the context of carbonyl compounds, because if this R group here is a hydrogen, so that's a functional group present in aldehyde known as a formyl group. So the pattern is if you try to replace it with carbon, so in this case you have two carbons, one from the carbonyl carbon here, another with the alkyl chain. So you name that according to its original carboxylic acid. So if you try to name it as the carboxylic acid, it's known as ethanoic acid, right? So how do you determine the acyl name? Just have to replace the ic acid with il. So it's ethanoyl portion. So utilizing the Latin name, so you just have to remember this particular equivalents. So for meth it's form, for eth it's acet, for prop it's propion, for but it's butyr, for pent it's val, and the pattern continues. So that is why ethanoic acid is also known as acetyl, or ethanoyl is also known as acetyl, for methanol is also known as formyl. So it's derived also from the common name of the compound. So for a 3-carbon derivative, so originally it's called propanoic acid. So to determine the name of the structure or the acyl structure here, so just remove the ic acid, then replace with YL. So that's propanoyl. And for benzoic acid, it's benzoyl. For the reactions of carboxylic acid, initially we have this preparatory reaction. So these are we prepare carboxylic acids in the laboratory. So first we have alcohol or aldehyde oxidation. So take note this is a primary alcohol and an aldehyde. So by utilizing Jones reagent, so Jones reagent is chromic trioxide in sulfuric acid to form chromic acid dissolved in water, they will be converted up to carboxylic acid. Again, this is not possible just by utilizing mild oxidizing agent, for example, pyridinium chromochlorate. Another preparation is alkyl benzene oxidation. So the only difference is that if you want to prepare um, alkyl carboxylic acid or alkanoic acid, you can utilize this oxidation. However, if you want to have the carboxylic acid directly bonded to a benzene carbon, you have to perform this alkyl benzene oxidation. So in this case, what if ever you have a benzene ring in which there is an alkyl chain directly attached to it, in the presence of yet another strong oxidizing agent, in this case potassium permanganate, it will be converted to benzoic acid. Another preparation for carboxylic acid is by utilizing Grignard reagent with the starting material of carbon dioxide. Try to remember carbon dioxide has this particular structure, so you can imagine that carbon dioxide contains two um, carbonyl group in which Grignard reagent can attack. So what happens is that one of the carboxyl group in carboxylic acid is converted into a hydroxy group, and the R group is attached to the carboxylic acid to produce also an alkanoic acid. So you have two preparatory reactions to create alkanoic acids. Another reaction for carboxylic acid is salt formation. So whenever you encounter salt formation, it implies we are talking about the acidity of carboxylic acid, so therefore the ionizability of this particular hydrogen. And take notice that carboxylic acid are mildly stronger acids as compared to other functional groups such as alcohol, which is why the hydrogen can be replaced with regular or common alkali bases. So in this case, you just have to remove hydrogen, then replace it with sodium to produce the carboxylic acid salt. So take notice that for salt formation and esterification, they are very almost similar. The only difference is that instead of a hydroxide, this is a hydroxyl. But you can see the pattern that you just have to replace this portion of the structure with the hydrogen of the carboxylic acid. So the only difference is that you'll produce a salt if you utilize alkali bases, but if you utilize alcohol, you can create the first um, derivative of carboxylic acid known as esters. So esters are R, C, and O, and also R. So take notice that this is the original carboxylic acid, and the hydroxyl group is replaced with an R group. Another subtype of this reaction is lactone formation. So lactones also contains an ester functional group. So we have the carboxylic acid derivative directly bonded to alkyl chains. The only difference is that the carbon loops around itself to form a closed cyclic structure. So take notice that for this particular reaction, you need to have an alcohol and a source of carboxylic acid. So this example contains both of them. So we have a carboxylic acid in this terminal carbon and an alcohol at this other terminal carbon. So for lactone formation, because this is a cyclic structure, we need the common type of compounds that can produce this type of reaction are those that contains 4 and above carbon. So this is just to reduce the strain imparted by the cyclical nature of this structure. So try to remember that for esterification and also for salt formation, the byproduct is also water. So this is why this reaction also condensation reactions. So another reaction is saponification of esters. Try to remember esters are derivatives of carboxylic acid. So these are formed through the additional reaction of carboxylic acid and alcohol, which is why this is the reverse reaction because you start with an ester and you produce the carboxylic acid now in its salt form and the original alcohol. So the only reagent that is needed is the presence of an alkali base. For example, this is sodium hydroxide. So what happens is you try to remove the alkyl group here and replace it with the metal, creating the salt of the original fatty acid, and the byproduct is alcohol. So this reaction takes place in water and in the presence of thermal energy. So I'd like to focus more on the structure of this salt of carboxylic acid. So saponification of esters is named as such because the final product of this particular structure is soap. So soaps are nothing more than this or have this particular genetic structure. It contains the salt of carboxylic acid and a long hydrocarbon chain. The reason why soaps are effective is because of these two parts. This part is very polar, so it can bind to other polar um, substances. This part is very nonpolar, so it can also bind to other nonpolar substances. We call substances such as this that could bind to both polar and nonpolar as amphiphilic. So the minor product of this reaction is an alcohol. Another reaction is a monolysis of esters. So this is another way for us to create a derivative of carboxylic acid known as amides. So you start with an ester and you replace the OR group with an amine to form an amide. So the minor product of this reaction is also an alcohol. So it's called a monolysis because you are trying to cleave the ammonia reagent just to attach it into the ester. So another reaction of esters is alkylation by a Grignard reagent. So what happens is that you start with an ester and you form an alcohol, particularly a tertiary alcohol. So Grignard reagent has this particular format RMGX, so take notice the colors here. So what happens is that Grignard reagents remove this oxygen, then replace it with whatever R group is present, so in this case twice, because carbonyls have two bonds, so it can give it one for each alkyl chain, and the R group initially present in the ester, so it's removed into a separate compound. This is a minor product, which is also an alcohol, and attaches a hydrogen present in the solution. So this is the source of the alcohol in the major or final product. So another reaction of ester is a reduction of esters. So take notice that carboxylic acid has 3 bonds to oxygen. So reduction is any reaction that would remove or reduce the number of carbon-oxygen bond. So what happens here is that the alkoxy part of the ester is removed into a separate alcohol, which is our minor product, and it's replaced with a hydrogen. And this carbonyl group is destroyed, so it's converted into a hydroxyl group, and the remaining bond is given to another hydrogen, which is why the product is a primary alcohol. So another reaction, in this case, we attain another derivative of carboxylic acid known as acyl halides. So acyl halides contains an acyl group and a halogen. So the way you produce this derivative of carboxylic acid is you start with a carboxylic acid and react with thionyl chloride. So you remove the hydroxyl group and replace it with the chlorine or the halogen present in thionyl chloride. So the minor products are hydrochloric acid and sulfur dioxide. So for acyl halides, it's also known as acid halides because of the fact that these are acidic substances. In which case, if you try to dissolve it in water, it will produce back the carboxylic acid. So take notice that the chlorine in the acid halides will be replaced with the hydroxyl group even in very weak bases such as water, indicating that this is an acidic substance. So the way we name acyl halide is that we name it according to this particular pattern. We name it according to the acyl group. In this case, take notice this is a 2 carbon containing acyl. So we can name it as acetyl or ethanoyl. Then name the halogen present, in this case chloride. So it has the acyl halide format. So ethanoyl chloride or acetyl chloride. Take notice that there is a space between the words. Another reaction is amide formation of acid halide. So try to remember this is acidic. So in the presence of a basic ammonia, you can replace chlorine here with the nitrogen to produce an amide. So the way we name amides are is that we name initially the acyl group and attach the word amide. So this is acetamide, indicating this is 2 carbon containing. Also, they can be named as ethanamide. So the minor product is ammonium chloride. Next, we have acid anhydride formation. So acid anhydride formation is the condensation reaction of 2 carboxylic acid. So take notice that the hydrogen of one carboxylic acid will fuse to the hydroxyl group of another carboxylic acid and unite together to form this anhydride functional group. So the way we name acid anhydride is that we name first the alkyl chain present on both sides of the anhydride, then affix the word anhydride. So for example, in this case, these are 3 carbon containing alkyl chain. So this is propanoic anhydride. So these are 2 carbon containing carboxylic acid. So it's ethanoic anhydride. So these are what we call symmetric anhydride because both alkyl chain are the same. So how about if it's asymmetric, meaning the alkyl chain on one side is different from the other. So we cannot utilize this particular pattern. So you have to name it one by one. So this is 2, so that's ethanoic. This is 3, so that's propanoic. And you arrange them according to alphabetization. So E precedes P, so it's ethanoic, propanoic, and the word anhydride. So one unique fact about anhydride is that you can perform internal reaction, meaning both carboxylic acid is found on the same molecule on both sides. So they can fuse together through condensation reaction, so to create this particular anhydride, cyclic anhydride structure. So for anhydrides, they are very reactive. So they can react with water, with alcohols, and with amines. So if you react with water, you cleave the anhydride, then you attach a hydroxyl group on one part and a hydrogen on the other part to produce the original carboxylic acids. If you react it with water, the product is the original carboxylic acid plus an ester. But if you react with an amide, you produce one carboxylic acid and the other is an amide. So the reaction of carboxylic acids are very myriad, but it boils down to observing patterns. So you just have to remember that the common derivatives of carboxylic acids are esters, acyl or acid halides, acid anhydrides, and amides. So in terms of reactivity, take notice that this is in terms of decreasing reactivity. So acid halides are the most reactive. Next, acid anhydrides, then esters, then amides. So they can react with the following reagent, either with water, alcohols, and ammonia. And the reaction is named according to the breakup of this particular nucleophile. So water, the process is known as hydrolysis. For alcohol, it's alcoholysis. For ammonia, it's ammonolysis. So in this case, you react water with acid halides, acid anhydrides, esters, and amides to produce the original carboxylic acid. So for acid halides, we have carboxylic acid plus hydrochloric acid. For acid anhydrides, you produce 2 carboxylic acid. For esters, you produce 1 carboxylic acid. The minor product is an alcohol. And for amides, you produce the original carboxylic acid plus ammonia. So take notice that the major organic product for hydrolysis is the original carboxylic acid plus a specific minor product for each case. Moving forward, if you react with alcohol through the process of alcoholysis, you produce initially an ester with a minor product such as hydrochloric acid if you started with acyl halide, a carboxylic acid if you start with acid anhydride, and an alcohol if you started with an ester. So amides, as the most non-reactive, does not produce reactions with alcohol and ammonia. Just to complete the table, for ammonolysis, the major product is an amide. So the minor product, if you start with acyl halides, is ammonium chloride. If acid anhydride, a carboxylic acid. For esters, the minor product is an alcohol.